Okay. Your 1.1 times 10 to the fourth newtons per coulomb is the same as 1.1 times 10 to the fourth volts per meter. Okay. Now, if you got a couple of meters of wire here, resistance wire, such that 1,000 volts would result in a current of 1 coulomb per second, why does a voltage result in a current? Well, it's because having this voltage between the two ends of the wire creates an electric field in the wire. If it's a uniform wire, it'll be a uniform electric field. And that electric field accelerates charges. And that's where conduction comes from. We did that 3 weeks ago. Okay? So you need to understand that model and the implications. We did a lab where we talked about that. Okay? You had problems where we asked you to work things out related to that model. Okay? So what happens is you spread this voltage out over a longer distance, well, you get a smaller field, and whatever this wire is constructed of, quantum mechanically and all kinds of things in a more sophisticated conduction model that you don't have to worry about, the material of the wire dictates how much current density you're going to get from an electric field, given electric field. Okay? So you want to understand that. Okay, so if you had 1,000 volts, you'd create a bigger electric field than you would with 1.1 volt, right? Because you're spreading 1,000 volts out over if you spread 1,000 volts out over whatever this wire is, you're going to get this much current. That is incidentally 1 amp, right? But I want you to think in terms of how many coulombs per second, so I don't use amps right now. Okay. Now you got 1.1 volt. Well, that's about 1,000th of this, right? Actually, it's 1 over 909.090909 repeating. Yeah. Okay? But, about 1,000th, ballpark 1,000th of the voltage, that's going to give you 1,000th of the electric field spread out over the same circuit, which is going to give you 1,000th of the acceleration on the free charges, okay? Which is going to give you 1,000th of current, okay? So we have to understand that in order to understand what goes on here. So you have .1 volts, current's going to be okay, and I said 909.9 because I got my proportionality backwards. It's actually 1100. Well, yeah, it's going to be 1/900. Or 0.011. Coulombs per second. Okay? Now again, the reasoning is you got much less, about 1,000th of the potential difference spread out over the same circuit. So you get about 1,000th, but more exactly 0.0011 of the current. Okay? Now that allows you to calculate the resistance in ohms, but I don't want you to think of a formula between potential difference, current, and resistance until you understand what it means. Okay? Okay. And I've got to remember, when I was in Las Vegas last week, went to a museum, had a really great display on mathematics, and it's used in different fields. You saw a lot of multivariable calculus in the screens, and a lot of really neat diagrams and stuff. But there's a thing about ohm. And ohm did something, and I can't remember right now what it was, but as soon as I stop and think about it, I will. Something really neat that I never knew he did. But he worked out these relationships experimentally, I think. He came up with Ohm's law, which he could have used to get these answers without understanding any of this. Okay? So that's going to be important, but I want you to think, again, in terms of the fundamental quantities. So now we're going to get to what happens with a capacitor. Okay, with a capacitor, if you got a switch here and this thing is charged up and you got this resistance wire, right? Well, current's going to start flowing. Just a little bit of current, about 1,000th of a coulomb every second, right? Okay? Now you've only got a microcoulomb of charge on here, right? So how long is it going to take for 10% of the charge on this capacitor to be transferred? Okay? What's actually going to happen here is 10% of this negative charge will migrate over to here. How long is that going to take? If charge is migrating at this rate.